So we have been looking at activating groups. We have seen that the methyl group of toluene is electron releasing and it's an auto para director. This is an auto para director, and the reason being is that the activation energy for the auto para attack of the sigma complexes are significantly lower than those of the meta attack. The same is true of methoxy group in anisole. The methoxy group in anisole activates the ring 400 times more than benzene. Of course, we expect that through induction, the methoxy group is electron withdrawn. Through induction, the methoxy group is electron withdrawn. However, the methoxy group can donate electron density through resonance. Okay. Of course, if you look at all the resonance structures, you can see that you will see that the structures that contribute the most to the resonance hybrids are those in which charge is minimized. Okay, those in which charge is minimized, and also those in which all the atoms obey the octet. Now, you can see here that if you look at the methoxy group here, activates the ring so strongly that polysubstitution is difficult to avoid. You really can't stop at just substitution of one bromine atom. It actually substitutes at all the auto and para positions. Okay. Now, the resonance stabilization effects affects the radioselectivity. As you can see here, for the auto attack, the positive charge is next to the oxygen, which can be stabilized by resonance. So you see that this structure here is going to be the most stable. That's going to be the most significant resonance form. But on the other hand here, you can see that the positive charge is never on the carbon that bears the methoxy group. However, in the case of the para attack, you can see that the methoxy group is attached to the atom that bears the positive charge. Okay. Now, how will the methoxy group affect the transition state? We can see that because it's able to stabilize the positive charge, there is a significant lowering of the activation energy. See, there's a significant lowering of the activation energy in the case of the auto and the para attack. Of course, it's greater in the auto and in the para. Sorry, you can see it is greater in the auto attack, but in the para is lower. The reason, of course, is because in the para attack you have less steric hindrance. You have less sterics, but here you have a lot of steric hindrance, and so the activation energy is a little greater. Now, all activators are auto para directors. All of them. All activators are auto para directors. Okay. The only exception is if you have a chlorine, which is a deactivator, it's also an auto para director. So in this kind of case, you can see, if you want to make this kind of product, you can see that it's a 1-4. It is a 1-4 relationship. Okay, so the first thing you want to do is introduce this acyl group, and then you can do a clemency reduction. See, just like as you can see here. So the first thing you want to do is introduce the acyl. So you introduce the acyl, you do an acylation, and then you do a clemency reduction. In the presence of the zinc mercury amalgam into the Cl. And if you want, you can always reduce. You can always so you can see you put and once you introduce that, then the next thing you want to do is to put the NO2 group there. You see, so that's basically what we're doing. Then of course, after the Clemmensen reduction, you can now do the nitration. You do the para nitration as well as the auto nitration. Okay, so we know the activation groups. The activating groups, nitro group is an electron withdrawing group through both resonance and induction. Okay, that's because it bears a positive charge. It bears a fully developed positive charge. And see, and so it's a deactivator. That's how you know deactivators. They bear a positive, either fully developed positive charge or a partial positive charge on the atom that is directly linked to the ring. Withholding electrons from the ring deactivates it. It deactivates it. It deactivates it, you see. And basically, so through induction and resonance, they're making the ring less nucleophilic. As you can see here, you can see the nitro group. You can see that the electron density is withdrawn from the ring through resonance and induction. So you have an electron withdrawing group that withdraws electron density from the ring through resonance and induction. With withdrawing electron, will make the transition state less stable. Of course, it really depends, because if you withdraw electron density from the intermediate, they're going to make any positive charge on the ring. You're going to make it less stable. Okay, so you're going to make it less stable. See, and you can see, interestingly, you can see that the positive charge resides at the ortho and at the para positions, but never at the meta. The meta position doesn't bear the positive charge. That's something you need to note here. Okay, so upon auto attack, you can see that the positive charge is in a very bad position because it is next to an electron withdrawing group, and so this intermediate is destabilized. Okay, but on this side, you can see that the positive charge is stabilized by resonance. You see, stabilized by resonance. But here, the positive charge is destabilized. It's destabilized because of the electron withdrawing effect of the nitro group. See, and that is why electron withdrawing groups are meta directors. They're meta directors. Okay, they're meta directors. The meta position, as you can see, predominates because the other positions are deactivated. As you can see here, the positive charge is on the carbon that is connected to the electron withdrawing group. We know that positive charges are stabilized by electron donating effect groups, not electron withdrawing groups. You see, as you can see here, so that's why the activation energy is very large. So here the positive charge is only stabilized by resonance, right? It's not destabilized by the electron withdrawing effect of the nitro group. You see, and that's why the activation energy here, EA, is the lowest here. EA is the lowest. Okay. Now halogens are electron donating groups. Halogens are, even though they are slightly they are actually ring they are deactivating, but they are auto para directors. So all electron withdrawing groups are meta directors except halogens. Halogens, even though they are weakly deactivating, but they are auto para directors. That's because they can donate electron density through resonance. They have lone pairs of electrons which they can donate into the ring through resonance. So make a note of that. That even though we said that all electron withdrawing groups are meta directors, but in the case of chlorine, which is a deactivating group, because it can also donate electron density through resonance, it is also an auto para director. So it's just one of the exceptions. Halogens can donate electrons through resonance, and as a result, you see they are auto para directors. As you can see here, so the positive charge is next to a chlorine which can be stabilized by resonance. See, the positive charge is next to a chlorine which can be stabilized by resonance in the case of the para attack and the auto attack. Okay. So if you compare the energy diagrams for the following reactions: nitration of benzene, auto-nitration of chlorobenzene, and the meta-nitration, you're going to see that the meta-nitration of chlorobenzene is going to have the highest activation energy, while the para-nitration is going to have the lowest activation energy, just like for reasons that we explained earlier. Now, determine the directing effects of a substituent. Let's summarize the directing effects of more substituents. Strong activators. What makes them strong? They can donate electron donating through resonance. And how you know that they are strong activators is that the atom that is connected to the ring has lone pairs of electrons. You can see lone pairs of electrons, lone pairs of electrons, lone pairs of electrons. All these are strong activators. Moderate activators, right? They have electron donating. They electron donated through resonance, but the lone pair of electron is not entirely available to the ring. You can see that the lone pair of electron is not entirely available to the ring. It can be delocalized away from the ring. So this kind of systems, have electron. They have moderate activators. And of course, anisole, which is one of them, is an alkoxybenzene, which is one of them, is also a moderate activator. The weak activators are those that donate electron density through hyperconjugation, like the alkyl groups. The alkyl groups, those are all weak. But the weak deactivators are the halogens. See, even though they withdraw electron density from the ring via induction, in other words, they have an electron withdrawing effect from the ring by induction, they can also donate electron density into the ring using resonance. Okay, so these are the exceptions. These are the only weak deactivators which are auto para directors. The halogens, the chlorines, the bromines, the iodines, all these are, even though they are weak deactivators, they can donate electron density through resonance. So to be able to determine the directing effects, moderate deactivators, on the other hand, if you look at moderate deactivators, what makes them moderate? See, they have a partial positive charge. A partial positive charge on the atom that bears that is connected to the ring, while strong deactivators have a fully developed positive charge. Okay, and also this one bearing three halogens. Okay, that's how you know the strong activators. They have an electron, a positive formal charge. Most of them have a positive formal charge, or they could bear 3 halogens on the carbon that is directly connected to the ring. Okay, so for compound below, determine whether the group is electron withdrawing or electron donating. Of course, we can see that this is going to be electron donating via resonance and going to be an autopara director.